Okay, we're live. I hope you guys had a good weekend so far, and I imagine some of you are studying tonight. There are lots of activities this weekend, so hopefully you'll have some time tomorrow night. And I want to start off by just reminding you that tomorrow night I'm going to be at Origins to answer any questions you might have. I'm not doing a review session per se. Like I don't have an agenda. I don't have these things to go through. I'll just be there. If there's only a few of you, I'll just pop around. If there's more of you, we can go into the back and I can use the whiteboard. All right, so let's take a look. Something's going on my, sorry, give me just 1 second. Something happened to my setup. I don't know what happened. I hope you can still see me. I hope it's still going okay. There's nobody in the Hangout right now but me, so I'll just start on the questions. So far, we only have one question. Or actually, no, that's not true. Looks like it might be 3 questions. So I'm going to go through it and answer those 3 questions, and then I guess we'll see where we stand at that point. Okay, so Sabrina had a few questions, and numbers 1, 12, and 16. So I'm going to share my, oh, do I have that? I might even have, I didn't remember if I put that one on my computer, because then I could show it to you. Oh, my computer is doing funny things. I think it's here. Okay, good. So why don't I share that one? And I can solve it. Okay, I'll make it a little bit bigger so it's easier to see. Here we go. Okay. So let's start with number 1. I think that was the first question. Yeah. So number 1 said, which of the following electronic configurations accurately represents the ground state configuration of the iron 3, Roman numeral 3, ion? And if you remember the 3, it only applies whenever you see transition metals. That's when you get Roman numerals. And the 3 would represent the charge on that iron. So for metal ions, of course, that's a 3+. So let's look at what the charge, or not the charge, but let's look at what the electron configuration would be without, look at what it would be without being an ion. Okay. So iron, all right. Iron, which is Fe, I forgot this was doing funny things, has 26 electrons. Well, let me rephrase it. It has 26 protons. And since we're looking at the periodic table, that would just equal out to 26 electrons. Okay. So if we wrote this out, 1s2. And then we go to 2s2, 2p6, 3s2, 3p6. Now it's in the 4th row, 4s2, and 1, 2, 3, 4, 5, 6. It's 6 over So, and it's the fourth row, which means it's actually 3D. I believe that's 6. 6. Okay. So that is and just to make sure it's 26 electrons. 2 plus 2 is 4, 4 plus 6 is 10, 10 plus 2 is 12, 12 plus 6 is 18, 18 plus 2 is 20, 20 plus 6 is 26. Okay, so we're happy. This is a neutral iron atom, and it would be 26 electrons. Now, whenever you have, whenever you have an ion, it loses electron. Oh, no, I'm sorry, whenever you have a cation, a metal, transition metal, it's going to lose electrons, valence shell, and it's going to, a cation means it's going to lose electrons. Electrons are negatively charged, which is why you end up with Fe3+. So the interesting thing is that because it's a transition metal, this is where it gets funny, and it's going to lose valence shell electrons. And what are valence shell electrons? They are the electrons in the outermost energy level. So if you look at this electron configuration here, which is the outermost shell? And it's not 3, it's 4. So it has to lose those electrons first. And there are 2 of them. So this 4s2 goes away. It loses both electrons from 4s2. So it is no longer, there are no longer any electrons in the 4th energy level. So in that 4s. Now that it's lost those electrons, it then goes to the next outermost energy level, and the energy levels within, the next subshell, the next orbital within a shell, it S, P, D, and F. That's how it starts, the closest to the nucleus to the outer, like S, and then P, and then D, and then F. It's all out there, like if this is your nucleus down here. So there are no F, but we have D. So it has one more electron it needs to lose. So it's going to lose 1 from the D subshell to go to 5. So then we have 1s2, 2s2, 2p6, 3s2, 3p6, 3d5. And let's see. I sure hope that's the answer. C, 1s2, 2s2, 2p6, 3s2, 3p6, 3d5. There it is. Okay. So it is the, that's the correct answer for number 1. So hopefully that helps you on that one. Let's go to 12. All right. Radium reacts with water according to the above reaction. What volume of hydrogen gas at standard temperature and pressure is produced from 0.100 moles of radium? Okay. So let's go ahead and put that on the bamboo paper. Okay. Oh, by the way, this was number 1 on the multiple choice. And then this would be number 12 on the multiple choice. And we have the reaction Ra, oh man, plus 2 H2O. How nice it was balanced for you. Goes to Ra, radium hydroxide, plus H2. Okay. Excuse me. And we want to know how much hydrogen gas at STP. And we start with 0.100 moles of radium. And so let's build our bridge. For every one mole of radium, we have 1 mole of H2. And the volume, okay, for every, well, we're at STP, for every 1 mole of H2, that's 22.4 liters of H2. And it's just asking you for volume. And so basically you're just multiplying 0.1 times 22.4, which comes out to be 2.24 liters. Done. Of H2. I suppose I should put that in there. Number, unit, substance. Okay. And that should be the right answer. And let's go back to the test. And the answer is A, 2.24. Excelente. All right. And the last one on your list was number 16. The boiling temperature of neon is less than that of krypton. Which of the statements below indicates why this is so? C, krypton is more polarizable than neon. This one's kind of actually cool. So krypton forms stronger dipole forces, no. Stronger hydrogen bonds, not a chance. And krypton, liquid has a higher density than neon liquid. Yeah. All right, I don't really know how to describe this. I don't need to draw anything, I suppose. Basically, this boils down to the size of the atom. And neon and krypton are in the same family. And neon is very small compared to krypton. Or I should just say krypton is larger than neon, because they're actually not that far apart. They are monatomic gases. They're noble gases, so you're not going to have a lot of forces between them. The only force you have, being non-polar molecules or atoms, is that you have London dispersion forces. And whenever you have London dispersion forces, the larger the atom, the more likely it can do an induced dipole. And when it does that, the larger it is, it's polarizable. Induced dipole means it creates this momentary dipole. The electron clouds push into each other, and when they push into each other, it pushes the electron cloud, because electron clouds repel each other. When an electron cloud pushes into another atom's electron cloud, it pushes that electron cloud away. And in the atom, when one side of it, when the electrons are moved away from that side, it becomes more positive. And so you end up with a positive side and a slightly positive side and a negative side. And you end up with, again, this momentary dipole, induced dipole. So it's the phrase is that it is polarizable. So when it is polarizable, it creates a momentary dipole. It is an induced dipole because they pushed into each other. It's something that didn't exist before. And then you can get some stronger bonds within the London dispersion. So the melting point and the boiling point, those characteristics that rely upon those forces are then higher melting point, higher boiling point. So hopefully that answers your question about number 16. It's the same concept when we had the I2 versus Cl2 or Br2. Why is bromine a liquid? Why is iodine a solid at room temperature? And those are because of those, as you move down the table for those halogens, they are larger molecules, so they are more polarizable. So, all right. So I think I'm finished with Sabrina's questions. Oh, good. There's other questions. Well, let's take a look at those. All right. Diana had a question on number 8 on the multiple choice. So let's take a look at that. Number 8. This is a good one. These are one of the tricky ones. Like, are you reading it? Are you paying attention to what's happening? A lot of people are getting tricked up on these, which makes me want to put it on the test. Because I don't want you guys to get tripped up or tricked on this on the end of the year, the actual AP exam in May. So let's take a look at this. We'll put it on the bamboo tablet. All right. So the question says the volume of distilled water that should be added to 20 milliliters of 3 molar sodium hydroxide to prepare a 0.2 molar sodium hydroxide solution is approximately, and let's make a new, I'll open this up to a new page. Okay. So multiple choice number 8. And let's change it like this in color right here. Okay. So you have a existing solution that has a, so molarity 1. It's a dilution, right? You're adding water to something to dilute it. So your initial molarity is 3.00 molar NaOH. Okay. And the final molarity, M2, wow, is equal to 0.20. Oh my goodness, I cannot write this out. I'm getting frustrated. Let's try this again. 0.200 molar NaOH. And the initial volume, V1, is equal to 20.0 milliliters. And we're looking for V2, right? So our equation is M1 V1 is equal to M2 V2. We're looking for V2, so that's equal to M1 V1 over M2. Okay, M1 is 3.00 molar. V1 is 20. I can't really tell. Oh my lord. 20.0 milliliters. And M2 is 0.2. Oh my goodness, 200 molarity. All right. And this one is the molarity on the bottom, the number 0.2 goes into 20 100 times, right? So it's 1. Is that right? Am I getting this wrong? 100? That's right. Yeah. If we move this over 1, move that over 1, 2 into 200 times. Okay, good. 100 times. Okay. So now we're left with V2 is equal to 3 times 100, which leaves us with 300 decimal point milliliters. Okay. And then you say, hey, I'm done. Look, it's V2. I solved for V2. It's 300. That's one of the answers. Yay. Now, let's go switch back to the problem. And we take a look at this. And you'll notice that it says the volume of distilled water. You are solving for the water. Okay. If you do that equation, the actual equation has you solving for sodium hydroxide. Like there's a solution in there, sodium hydroxide in there. The question says the volume of the distilled water. Like you can't just solve for V2 and get water because there's sodium hydroxide in there, right? The molarity, moles per liter, moles of sodium hydroxide. So that should clue you in that something's off. And then it said the volume of water that should be added to 20 milliliters. So you have 20 milliliters of the 3 molar sodium hydroxide, and then you added water to it to dilute it. So there was already 20 milliliters in there. So what you had to do is you had to subtract 20 from your final answer because your final answer just gives you the final volume. That question did not ask you for the final volume. It asked you how much water you added. So 300 minus 20 is 280. So that question, it's a question that so many students get wrong. You have to pay attention. You have to read them carefully. Don't just think to yourself, oh, I know what this is, and just start solving without really thinking about what it's asking for. Major place that AP Chem students lose points is not answering the question that was asked. It's not just for this one, it's for all of them. If you don't answer the question that was asked, you'll lose points, and that's a major bummer. You may totally know it. Like, this is not really an advanced concept. This is just asking you to read the question and pay attention, okay? So that's why the answer is C, 280. All right, good. We're done with that one. All right, the next, oh, interesting. Faith would like to see 4B, and Sammy would like to see 4A and 4C. So basically, I'm doing A, B, and C. I might as well start with 4A. Do that first, and then B, it could probably be kind of related. So let's just go ahead and go to 4A, and then we'll talk about B, then we'll talk about C. So what does 4 say? 4. A 2-gram sample of limestone dissolved in hydrochloric acid, and all the calcium present in the sample was converted to calcium 2+, the ion, the aqueous ion. Excess ammonium oxalate ion, NH4-2C2O4 aqueous, was added to the solution to precipitate the calcium ions as calcium oxalate, CaC2O4 solid. Wow, I gave you all those polyatomic ions. I am not going to give you those polyatomic ions on the test. I'm going to make you work for that, because that's something you should all know by now. You all got 100% on the quizzes. So I definitely encourage you to go back and double check those. Okay, so we're basically doing A, B, and C. You're just working through the problem. We can do this, right? Okay, so I'm going to share my Bamboo tablet again. And we're going to go to the next page. And we're going to say number 4. Wow, on the free response. And start with A. And write the net ionic equation for the precipitate that is produced. Okay, the precipitate, you could, and again, a lot of times you can just go backwards. Your precipitate was calcium, C2O4 solid, okay? So you remember from net ionic equations, you cancel out everything except for the ions that are involved in the equation. And when it's a precipitate, it's a super simple equation. There are only 2 reactants and 1 product. Okay, so you look at it and you know there are 2 ions involved. I should make these a different color is what I should do, huh? Let's make them orange. Orange sounds like fun. Nothing rhymes with orange. There's 1 ion for calcium, and here's another ion for oxalate. So then you look, what's the charge on calcium? Well, I even gave that to you in the problem. Calcium 2+ plus oxalate, C2O4. And of course, you've memorized it, so you know that that is 2-. And when they come together, you get the precipitate that was given to you in the problem. Oh, what am I doing? Writing the charge. Big no-no. Please don't do that. You'll lose points. CaC2O4. Okay, so a few things. 1, when you have the ions, you must put the charge on them. Okay, you don't have to necessarily put the parentheses around that, but it helps. You have to put the charge on it. When you do the product, the precipitate, you do not include the charges. If you include the charges, it will get marked wrong. Oh, and by the way, this will be a question on the test, on the free response. You do not have to put the state symbols. So like this solid right here. You don't have to do that. Some students like to do it, and that's fine, but it is definitely not, oh my goodness, I cannot write with this. I think I need to switch these out, get a new blue tablet. Okay. Some students like to do it, not a big deal. If you put the wrong ones down, I don't think you get marked off for it, but that's the problem. Remember I told you about contradicting yourself? There's not an emphasis on state symbols, but you never know. College Board has done some things recently. On the last test, they did something that they had said they wouldn't do in the past. So suddenly they changed it. There was like a policy change, and they didn't tell anybody. They said, oh, there was hints at it in the past test, but they didn't say what it was. So their policy in the past has been ignore state symbols. As a reader, I'm supposed to ignore state symbols. But they could suddenly say, hey, you know, this is a precipitate reaction. They need to know that that's a solid. So if you put an aqueous over here, that is clearly indicating you don't know that precipitates are solids. And maybe I'm supposed to mark that wrong. So unless you're absolutely sure, don't put the state symbols. It's just not worth it, okay? All right, so that's A. You can just, you just wrote the net ionic equation, done. 2 reactants, 1 product, period. You don't put all the other stuff in there. There was a hydrochloric acid, which was H and Cl, and you know, that's a strong acid. It dissociates completely. You're gonna have some of those ions on both sides. Doesn't matter, it's not in there. Ammonium, it's always soluble. Remember, ammonium, alkali metals, and nitrates. Ammonium's in there. Don't include it in there. Like, do I even care? I didn't even ask for the molecular equation. I just asked you for the net ionic. You know what the precipitate is, the solid, so it's right there. It's that simple, okay? All right, let's go on to B. So, and B says, write the net ion, or I'm sorry, describe the process by which a precipitate can be isolated, include a picture. So in this one, it's kind of more of a general question, but if you were to have this, right, it's dissolved in hydrochloric acid, and then you've added this other solution. So kind of what you're doing is you are, maybe if you want to give some steps, right, you're mixing all solutions together. And I'm going to abbreviate here. I'm hoping you guys are getting my abbreviations by now. You mix all solutions together. I probably just could have said mix all solutions. In fact, that's what I'm going to do because this pen is, this whole board and pen is messing me up. Mixing all solutions. Then you're going to pour through filter paper. You're going to pour through the filter paper. Then dry filter paper. Oh my goodness. My apologies. As I'm writing this and thinking about the answer, well, I would say that dry filter paper with precipitate. Okay, now I think that I kind of wrote this question a little bit on the fly. So this is pretty much it, except for the drawing, which I'm going to do in a second. But just remember that you had a mass of limestone to begin with, right? And then at the end, you need to get a mass. You've got to know how much you have. So even though, like, I probably wouldn't mark you off if you didn't say mass filter paper, because then it just says isolated. That's all it says. So you've got to mass it though, because then what you have to do, and you should have also like masked the filter paper to begin with. Then you mask at the end, you subtract out the filter paper, and you get the mass of just the precipitate. And then once you have that, then you can do your percentages and things, which goes into C right now. Okay. Okay. The precipitate was filtered, dried, and wow, I even said it. Oh my Lord. I must have been tired when I did this. I kind of gave you the answer to the B in C. The precipitate was filtered, dried, and weighed to, oh, I'm sorry, I had to draw the picture. Oh my Lord. I am not on a roll. Not on a roll today, just in case you're wondering. Okay, so basically all I'm looking for is that silly picture that we did in the lab. The more you see the stuff, the better, right? So, my apologies because I am not an artiste. Okay. And you had filter paper coming down in, and it was like, you know how you folded it? So there's these ridges in it. And basically, what I wanted to see in doing this was that, and you know, you could have, I suppose you could have, when you're pouring it in, down here you have, I want you to draw a little key. So you've got the ions that you know didn't go through. Okay, and then inside of here, I did a horrible job drawing. I will probably give you the picture, and you have to draw it in the picture. But you have to add, you know, remember this thing where you drew them. Okay, so these squares are here represent the precipitate, which in this case, precipitate would be the CaC2O4. So that's what these are. Okay, and these are in here. They were caught with the filter paper. Down here, the triangles that would be the ions that were filtered through. So you're looking at things like NH4 plus, other things that could have, you might have some H plus, you might have some Cl minus, something like that. Anything you could have drawn down that would have been fine. And basically this, of course, was everything mixed together. So like, use some red here. Number one, this is number one right here, right? You mixed everything together. Then you poured it through the filter paper, and that would be what you did here for number two. And then you dried the filter paper with the precipitate, and that is what this is right here, right? Okay, and then you mask it. But basically that's what I was looking for with the included picture. I was kind of hoping you would draw the picture, just go back to your lab and draw it. If I have you draw the picture, which I'm really leaning towards on the test, it's probably going to be given to you, just for the sake of brevity. Like I just don't want you to spend a lot of time trying to draw it. It's better if you just draw the symbols. Okay. Now we're on to C. My apologies, that took a little while. Okay. Okay, C. The precipitate was filtered, dried, and weighed to a constant mass of 2.43 grams. Determine the percentage by mass of calcium in the limestone sample. Okay, so you had 2.43 grams of calcium oxalate, right? Sorry, my phone was ringing in my pocket. Calcium C2O4, right? So you have 2.43, that's the precipitate. It wants to know really how much calcium was in the original limestone, right? There was no oxalate in the limestone. It was just the calcium was in there with other things. You use the oxalate to precipitate the calcium so you could collect it all and filter it out, dry it, etc. So we have to figure out how much, if you have 2.43 grams of calcium oxalate, how many grams of calcium is that? 2.43 grams of, so we make a bridge because bridges are fun. All right, good. Now it's a, you've got to do the grams to moles, because you're basically doing a gram to gram conversion, going through that net ionic equation. Pretty simple. I say that. We do it in Gen Chem. I guess that's why I call it simple. So first we need the mass of the calcium oxalate. So we have 1 calcium at 40.08 plus 2 carbons, 12.01 times 2, plus 4 oxygen, 16 times 4. And I ended up with a mass of the calcium oxalate of 128.10 grams calcium oxalate. Okay, and that's in 1 mole of calcium oxalate. Okay, and from our net ionic equation, for every 1 mole, I'm running out of room, of calcium oxalate, we get 1 mole of calcium. We'll call it the 2 plus ion. Not that it affects its mass at all. And for every 1 mole of calcium 2 plus, that is the 40.08 grams of calcium 2 plus. All right, so we run through that bridge. So 2.43 divided by 128.1 times 40.08, and I get 0.76. Oh, you can't even tell. This is just, this is fun. That's what this is. 0.7760 grams of calcium 2 plus. Okay, and it wants to know the percentage by mass. And so it's 0.760 grams calcium 2 plus over 2.00 grams of the limestone. We'll just, that's good. Time is percentage, so it's times 100 equals, so 0.760. Right. And so basically I, oops, times 100. I was going to say it wrong. I get 38.0%. 38.0. Yay! 38.0% calcium in the limestone. That would have been a lot faster if I could draw appropriately or quickly or easily. But hey, that is the answer, and that's the important part right now. So that was 4A and 4B and 4C. So hopefully, so I did, so I'm selecting 4B now. Faith, you had 4B. If you're watching this now, if you clicked on 4B, just went straight to 4B, I just covered 4B, so you just need to go backwards to cover 4B, because I also covered 4A and 4C, so I covered 4 all at one time. So that one's also done. So again, if you're watching this right now, just back it up a little bit. to where I talked about 4A and or where the questions for 4A, and you'll get the answer. Okay. Now, Diana, you have another one. Number 15 on the multiple choice. So let's take a look at that. Oops, I need to share the test. Okay. 15 on the multiple choice was, oh, the shape of the SO3 2- ion is best described as, okay, this is a multiple choice test. I am making it so that you have 1.5 minutes per, you have 1.5 minutes per multiple choice. So you have to think about this and how long is this going to take you and things like that. So you look at this and you could say, okay, the SO3 ion is best described as, and you're now going to say, okay, I don't know. It's an ion. It's got 3 oxygens. Probably a good chance that it could be maybe an expanded octet. It is in the 3rd period going down. Maybe it's not an expanded octet. I seriously doubt it, but it is an ion. Maybe it's giving it enough. So let's take a look and see what we've got. It says that we already know the answer is trigonal pyramidal, but you don't know that looking at it. You're like, I have no idea. Could it be trigonal planar? Maybe. Could it be tetrahedral? Maybe. Could it be T-shaped? Wouldn't that be fun? T-shaped has got a lot of lone pairs, and there's a lot of bonds there. Anyways, let's go ahead and start drawing and see what we come up with. So let's share that. All right, let's make us a new piece of paper. We have, multiple choice number 15. Okay. And SO3 2-. So let's talk about the math involved here. We have sulfur has a 6. Plus there are 3 oxygens. So that's 3 times 6. And then we have the charge, the ion, which is, so we're getting 2 electrons out of that. So we are basically coming down to 6 plus 18 plus 2. So 18 plus 2 is 20, 20 plus 6 is 26. All right. If you remember, the least electronegative element goes in the center, or sometimes it's the element that just makes the most bonds. In this case, you've got sulfur and oxygen. You would say, hey, they make the most, or they make the same number of bonds, except for that oxygen is in the 2nd period, will not have an expanded octet. The sulfur could potentially have an expanded octet. It also, so it has the potential to make more bonds, is basically what we're boiled down to. So, and if you think of this logically, if there's multiple of one atom, it's probably the ones on the outside. Okay, so I put sulfur in the middle. Okay, and I'm going to make a single bond to each oxygen. Okay. So already we have an issue because sulfur is just like oxygen. You would think it would have 2 dots on top, 2 dots on the bottom, and it would just make 2 bonds, 1 to each oxygen. However, there is another oxygen. So it's making another bond of oxygen. So right now we're kind of messed up a little bit. We don't know what to do about that. So I'm going to say -6. That's going to give us 20 electrons. Okay. Oh, Lord. Okay. So I'm going to fill in some dots here. And do so in such a way that it doesn't make these really lame lines. Okay, obviously that was not going to happen. All right, so I have that so far. And if you remember, there's 2 electrons that are coming in that are outside that were not part of the original structure. We include those in there, but we have access to those. So really, why don't we just put those here? That's what those 2 electrons are doing. They're completing the octet rule here. So we don't have to make any more bonds there. So that's kind of nice and easy. So that's 2, 4, 6, 8, 10, 12. So we have 12 electrons that we have just added to those 2 oxygens. So now we have 8. All right, good. So now I have 8 left. How are we going to do this? So you could do a few things. You might say, okay, with 8 left, I know that this one has these 2, this, oops, and it has 1 right here, right? And I know that well, actually, I'm just going to back it up because we don't know what this has up top here, okay? So I would say that we need to, I mean, with this is, remember, this is a terminal oxygen. Terminal oxygens aren't expanded octet. It's oxygens in the second phase. It's not an expanded octet anyhow. In this situation, we don't have an extra electron we can just throw out here, okay? So we need to put an electron. It's not just going to appear. It already made 1 bond here. We don't know what's happening with the electrons other electrons that are available here. So what I'm going to suggest that I think makes the most sense is that we would just turn this into another bond. So this electron right here went over here to form this other bond. Okay. So if we do that, then we have, we added another bond. So that's -2. That was with 6. I've got the dots here. 2 and 2 is 4. So -4 that are in the lone pairs on that oxygen. That leaves us electrons left over. And those 2 electrons, we would put on the center right here. Oh my Lord. I am going to do this without making lots of lines. I don't know how, but it's going to happen. So any left, when you're all finished with your Lewis dot structure, or you think you're finished with the Lewis dot structure, and you have electrons left over, they go on the central atom. And so you would add them right here. So there's your 2. So my explanation took longer than 1.5 minutes, obviously. So you've got to be quick about this. You've got to think, what's the most likely situation? And so that's the most likely situation. Now, you could start doing things like formal charges. And this is what I do when I have lots of time. If I want to go back and work on that multiple choice, take a look at it for a second, and I'm not sure, doing the formal charge is a great way of determining. And you need to look at the central atom. The central atom is kind of where it's at. You want the central atom to be as close to 0 as possible. So in this situation, sulfur has its total valence electrons are 6. That's the first number. Then you subtract out half of the bonded electrons. Half of the bonded electrons. So we have 2, 4, 6, 8. So we have 8 bonded electrons there. Minus the number of unbonded electrons. And that's that lone pair. So basically it's minus half of the bonded minus the number of lone pairs. Or not the number of lone pairs, the number of electrons that are in lone pairs. It's the unbonded. You get the idea. It's 2. So this is basically 6 minus 4 minus 2, which is equal to 0. Awesome. That formal charge on that sulfur is equal to 0. Oh, come on. Formal charge equal to 0. It's hard to ask for better. I mean, once you have that, you're good. Now, some students, I had some students ask me about this before, and they had a Lewis dot structure that basically had three oxygens, 3 single bonded oxygens with 6 electrons around each one. And so this is where, and basically they just went through and, I mean, they kind of knew the math. Oh, I forgot. If you have to draw the Lewis dot structure, don't forget to put the brackets around it. Like I did the math on it, but I didn't. So 2 minus. You got to put the brackets and the charge on it. Don't forget that. It's good to just practice all the time. Okay, so the math involved here, right? We had 26 minus 6 in single bonds. That gives us 20. And if we look at the dots, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Great. So that is mathematically, that is a valid structure. Is it the most likely structure? So sulfur's formal charge, 6 minus half of the bonded electrons. So that's half of 6 minus the unbonded pairs. So minus 2. So that's 6 minus 3 minus 2. So 6 minus 5 is 1. This structure right here gives you a formal charge of 1. And so it is not as likely as the other one. When you can get a formal charge that's 0, that is the most likely charge. Now, here's the other thing. It actually doesn't matter, does it? If it's single bonds or a double bond there, because is it not the same shape? So when it's shape, just make sure that you pay attention and don't get wrapped up in a detail like this. You get a trigonal pyramidal shape in both situations. So now you've wasted time in trying to figure out a different one. If it mathematically works, run with it. If it asks you to actually draw it, now you've got a situation. If it asks you if there are resonance, well, now you got to be careful, okay? Because in this one down here, in this picture down here, there is no resonance, okay? But the picture right here, there is resonance because there's 3 bonds that, and this double bond is really obviously shared across all 3 bonds. So it's that 4/3 bond order, shorter than a double bond, longer than a single bond, stronger than a single bond, weaker than a double bond. So this SO3 minus to SO3 2 minus is really got a lot tied into it, a lot of ideas, concepts, but the answer to that multiple choice number 15 is trigonal pyramidal. But it's a great teaching moment in that there are other things involved here that you can see. You know, there's resonance, there's sigma and pi bonds. The hybridization of that S atom is there are basically 3 things bonded on there. I'm sorry, 3 atoms bonded on there. So looking at it, I don't usually do it with lone pairs, but you're looking at like an sp2, but I probably wouldn't give you one with lone pairs. I'd probably just give you one with atoms if I did it. So in any case, that's the answer to multiple choice 15. So hopefully that makes sense to you guys, and I didn't go overboard with pushing pushing too many ideas at one time. All right. So that actually was a good number of questions for this review. I mean, that took basically an hour or a few minutes shy. I think this is a good moment for me to, I'm going to verbally list out some of the concepts that are going to be on the exam. Like I've gone through, these are the questions that will be on your exam, most likely. In the multiple choice, I'm most likely going to talk about successive ionization. Most likely there'll be a PES to take a look at and a mass spec to look at. Probably have a question, again, we're talking about multiple choice, hydrates, combustion analysis, kind of like empirical formula, oxidation numbers. There might be a balancing question, molarity, moles, liters, titration, dilution. I might have a question on electrolytes, or I might move it to free response. Also in multiple choice, like the ideal gas law questions. Remember that with density or molar mass, they're a little bit more complicated math questions that take a little bit longer. I'll try to only have one of those though, so that you're not spending an obscene amount of time doing that. Conceptual questions about Graham's law, diffusion or effusion of gases, and which should diffuse or effuse faster. I am going to put a question in there about the kinetic molecular theory, the KMT. You had darn well better review that. I had so many students saying, I don't know what the KMT is. I have forgotten what the KMT is. You need to figure it out. It's something you have to know. When you leave the gases, you need to understand those concepts. So bring it fresh to memory. I'm going to have a question on talking about alloys or doping, a question probably about sigma or pi bonds, metallic bonds, you know, that sea of electrons, ionic bonds, things to think about. Does it conduct when it's molten? I might have a question about graphite or shapes. Maybe I think I might touch on surface tension, capillary action, or viscosity, because that sounded like fun. For free response, I'm going to talk about gravimetric analysis. So that's that lab I just graded and handed back to you. Net ionic equations, drawings, giving you a data table, finding the limiting reactant, using stoichiometry. And I'll be talking about error. In fact, I'll probably be having, well, two of the free response questions are going to be you're going to have a question about error. So make sure you go back to those labs and review what the causes of error might be and what the effect of the error will be on your results. Another one of the free response will be collecting gas. So that, collecting gas over water, the fact that there's water vapor. I had students asking me about that. They weren't sure about what were in the retake. There was a question about gases collecting over water. It was hydrogen gas, and it asked you which one was more or least ideal, least close to the ideal, something like that, of the two gases. And so many students were not sure. They didn't know what the other gas was. Well, there's hydrogen gas, but I don't know what the other gas is. You're collecting it over water. There's always water vapor there, water vapor and hydrogen gas. So got to know that. Stoichiometry, like the theoretical, starting with something, you get the percent yield. Probably have a molar volume question there. Like if you have correcting it to STP, we did that in the lab. You're correcting your volume to what it would be at STP, and then using that to see how close you are to molar volume, because I kind of like that one. And then again, error. Where was there error? The bonding. I'm going to have probably several questions within the bonding free response where you have to compare molecules. You're probably going to have to draw one or two Lewis structures, talk about their shape, polarity, intermolecular forces, bond lengths, resonance, hydrogen bond, induced dipole, like the polarity with size. Probably talk about covalent network, right? Carbon, silicon, or quartz, SiO2. So Si or SiO2. Talk about ionic, the strength of ionic bonds based upon their charge or the ionic size. The smaller the ionic size, the stronger the bond. And I'm going back and forth. I don't know if I'm going to put the PES, honestly, in the multiple choice or the free response. Like it might be kind of like a small fourth free response, but as of right now, there's 20 multiple choice, 3 free response. You'll have 30 minutes to do the multiple choice, and that's the max. If you finish the multiple choice early and want free response, I'm fine with that. But 30 minutes is the maximum you will have for the for the multiple choice. Then you will have 45 minutes for the free response. That's the maximum you will have. I mean, the bell rings at the end of the period and we're done. Like, I'm collecting them. I'm taking them from you. If I see your pencil writing, I'll, mark it off or take points away or something. I'll be probably not super nice. Remember, this test does not count against you. It only helps you. So I'm not going to feel guilty about if you guys break my rules about, marking you down. Okay, so that's all I have to add to that. Again, as a reminder, at the end of this, in case you didn't hear at the beginning, I want to remind you all that I will be at Origins tomorrow night at 8. Not having a review session per se. I'm there to answer questions. If there are enough of us, we can get a back room maybe and have a whiteboard. Otherwise, if there's just a few of you, I'll just kind of bebop around in the area, drink some coffee, and answer as many questions as I can. So I'll be there for at least an hour, depending upon how my wife's feeling, 9 or 9:30. See how you guys are doing. I don't want to keep you guys up late either. So again, I hope you had a good weekend. I hope this was helpful, and I look forward to seeing maybe some of you tomorrow night. And if not, I hope to see some of you throughout the day. Just I don't want you to get to the test and be like, I don't understand something. Like, I want you guys to ask the questions ahead of time and then sleep on it, because sleeping will help you review the information. If you ask me in the morning on Tuesday, the chances of it sticking around are less likely. All right, that's enough of me lecturing. All right, thanks guys. I'll talk to you all later. Good luck, sleep tight.